Thank you very much. So I will take my opportunity of being the last speaker, so I would like to thank to the organizer for this fantastic event. So let's thank them all together. All right, so in my talk, I'm gonna talk a little bit about asymptotics. So the first part of the talk is a relation between random Young diagrams and representation theory of the symmetric group. So I'm going to tell you about a beautiful idea of Biane, who showed how characters of the symmetric group are strictly related with random Young diagrams, and how you can associate random Young diagrams with very nice asymptotic behavior. So you should think about the example of Plancherel measure. So this will be the most important example for us. And Plancherel measure is strictly related with the representation theory. So this is like a motivation for this generalization. And in the second part of my talk, I'm going to explain how this picture of representation theory can be rephrased in terms of the symmetric functions. And this symmetric functions framework will allow us to study a one-parameter deformation of the first part of the talk. And in the last part of the talk, I'm going to talk a little bit about the tool. So this will be the most algebraic combinatorics part. And here I'm going to also show you some open problems related with combinatorics of Jack symmetric polynomials and Jack characters. OK, so let's start from simple things. So in this talk, a partition and Young diagrams will always go together. So partition of the integer n is just a non-increasing sequence of positive integers which sum to a fixed integer n. So for me, n will be a parameter, and this parameter will grow. And whenever I think about partition, I'm thinking also at the same time about the graphical representation of this partition, which is a Young diagram. So this is a Young diagram which is drawn in a French convention. It's a Young diagram of size 24. It has 5 rows, so its length is equal to 5. And our problem is that we would like to understand asymptotic behaviors of random diagrams of a fixed size n when this parameter n is tending to infinity. OK, so this is our setup. And now I would like to tell you what is the relation between random Young diagrams and characters. So Biane, in his paper, he pointed out that there is a one-to-one correspondence between probability measures on the set of Young diagrams and normalized central positive definite functions on the symmetric group. So if you know nothing about positive definite function, don't worry, because this correspondence is here. So whenever you have a probability measure, you can define a function on the symmetric group which is given by this formula. So chi lambda is a character of the irreducible representation of the symmetric group, which is indexed by a Young diagram lambda. So a quick reminder for those who doesn't know representation theory of the symmetric group, there is a one-to-one correspondence between irreducible representations of the symmetric group and Young diagrams. So they are naturally indexed by Young diagrams, and you can use this formula to associate a character to a probability measure and vice versa. So the conclusion is that if you want to study asymptotic behavior of some random Young diagrams, we can study asymptotic behavior of associated characters. OK, so here is an example. So there are two examples of maybe most easy representations of the symmetric group. So the first representation is a regular representation. So clearly the character of the regular representation, it vanishes everywhere except identity. So regular representation is just an action of the symmetric group on itself by multiplication. And another very natural representation of the symmetric group, especially from a combinatorial point of view, is an action of the symmetric group on words with in alphabet with letters from 1 to big N. And again, this character is computed easily. It's a trivial thing. So here we have this correspondence between characters and probability measures. So if you start from a regular representation, an associated probability measure is the Plancherel measure. And in the second example, if you start from the Schur-Weil representation, then you get some probability measure that we will call Schur-Weil probability measure. Okay, so you see that the Plancherel measure, which is maybe the most studied one, this measure is associated with an extremely easy function, which vanishes everywhere except identity when it's equal to 1. So we can imagine that studying asymptotic behavior of this character is a pretty easy thing. So let me tell you a little bit more about the Plancherel measure. You already saw something about it. So you can also obtain the Plancherel measure as a push forward of the RSK algorithm. So I quickly remind that RSK algorithm, it's a bijection between permutations and a pair of two standard Young tableaux of the same shape. So if you take a push forward of the uniform measure on the permutation group through RSK, you obtain a probability measure on the set of Young diagrams, and this is exactly the Plancherel measure. If you like formulas, there is also a very explicit formula for the Plancherel measure, and this is a Hooke-length formula. So the probability of having a Young diagram lambda is n factorial divided by the product of Hooke lengths of cells squared. So here is a celebrated theorem of Logan and Shep and Vershik and Kerov, and it says that if you take random Young diagram and it's distributed with respect to the Plancherel measure, and you wonder what is the typical behavior when the size of your Young diagram is tending to infinity, then it turns out that these Young diagrams, random Young diagrams, they are very close to a certain fixed shape. Okay, so let's see some examples. So this is a random Young diagram of size 100. You can already see that its shape is not, okay, it has some kind of shape. Maybe you can see that there is some kind of curve here. It's maybe not big enough, so if you will play a little bit with them, then you can convince yourself that actually it converts to a certain shape, and this is the shape, which is a Logan shape and Vershik Kerov shape. So I stated this theorem a bit informally, but now I'm gonna do it a bit more formally. So let me introduce some simple concepts to put this formulation formal. So first of all, I want to compare Young diagrams. So I have to keep their area fixed in order to do this. So I'm going to define something which is called Anisotropic Young diagram. And this is simply just a polygon which is obtained from the Young diagram lambda by replacing each box of size 1 by 1 by a new box of size w times h. Okay, so here is an easy example. This is my Young diagram, and this is an associated anisotropic Young diagram. So in order to study asymptotic behavior, of course, I have to study rescaled Young diagrams so that I can compare them. So if I want to study random Young diagrams sampled by the Plancherel measure, the right scaling is that I'm just crushing this Young diagram so that its shape is fixed, but its area is equal to 1. So I have to crush it by square root of 1 divided by n. And another concept that you already saw on this simulation with random Young diagrams is that I started drawing my Young diagrams using French convention, which is very convenient for doing combinatorics. But if you want to do asymptotics, then it's actually a bit better to introduce a new coordinate system. So what you're doing, you're simply rotating your Young diagram by 45 degrees counterclockwise, and you stretch it by square root of 2, and this is a Russian convention. So now I'm interested in this thick black line, which is a profile of my Young diagram. And this is a function. This is just a function from real to positive real, which behaves like absolute value of x for big X. So now we have a theorem of Logan and Shep and Vershik and Kerov revisited, but now it's stated more formally. So what this theorem really says, it says that there exists a deterministic function from R to R with the property that if you look on the profile of rescaled Young diagram sampled with the Planchel measure, then they converge to this deterministic shape, and the convergence holds true with respect to the supremum norm in probability. Okay, so let's go back to the concept of associating a character with the random Young diagrams, and this is what Philippe Biane did. So he realized that this very special case of Planchel measure can be put into a much more general setup, and he defined characters with the approximate factorization property. So what are these characters? Basically, there are two conditions. So the first condition tells you that the character do not decay too slow. So this is the right order of magnitude. And it also says that if you look on the difference between character on a disjoint product of two partitions and a product of two characters, then the order of magnitude should be lower. So the right order of magnitude it looks like that. So we see it's not additive because there is this -2 factor here. So this is the definition of characters with the approximate factorization property. And theorem of Philippe is that whenever you have a family of such characters, then you have the law of large numbers. So you remember, with the characters, I have associated random Young diagrams. And the theorem says that if my characters has the approximate factorization property, then the profile of associated random Young diagrams converge to a limit shape. So let's go back to our two examples. It's trivial that the regular character has the approximate factorization property. And it's also very easy to see that if this big N in a Schur-Weil character has the same order of magnitude like square root of n, then this character also has the approximate factorization property. And in particular, Philippe computed an explicit curve, which is the limit shape for this family of random Young diagrams. So we can see that when c is equal to 0, this curve is exactly a Logan-Shep-Vershik Kerov curve, but for different parameters c, it looks a bit different. Okay, so this is a law of large numbers, and there is also a central limit theorem problem. So we would like to ask, can we say something more? If we already know that our random Young diagrams, they concentrate around some shape, can we say something about the fluctuations around this limit shape? So in order to make it formal, we have to study these quantities. So first of all, I'm looking on the difference between the limit shape and our profile, and I rescale it properly. So I have to multiply by square root of n. And then I would like to say that if I'm lucky, maybe my profile asymptotically behaves like that. So the first order approximation is this limit shape. And the second order approximation is some random Gaussian vector. So in order to do this, we need to study a suitable test functions. So these are just moments with respect to this delta n measure. And again, going back to our major example, which is the Plancherel measure, Kerov proved 16 years after the law of large numbers, he proved the central limit theorem for the Plancherel measure. So he proved that indeed, if you take random Young diagrams with respect to the Plancherel measure, then the fluctuations are Gaussian. Okay, so can we again find the right framework to put this example of the Plancherel measure into a bigger picture? The answer is yes. We just have to put a little bit more restrictive definition of the approximate factorization property. So note that Philippe Biane, he introduced these two conditions, and if you look on these conditions from the point of view of the probability, you can see that the first quantity is just an expectation of the reducible characters with respect to this probability measure, which is associated with the character. And this second condition is a variance with respect to this measure. So there exists a notion which generalizes expectation and variance for higher order, and it's called a cumulant. So cumulant of random variables is something which is measuring discrepancy between random variables, and it's given by this system of equations which is invertible. So on the left-hand side, I just have an expectation of a product of random variables. And on the right-hand side, I'm summing over all set partitions of n, where I have n random variables. And I have product of appropriate cumulants. So in our context, on the left-hand side, I just have a character evaluated in a product of disjoint partitions, and on the right-hand side, I have cumulants. So now, we can replace these two conditions by only one condition, and this is what Sniady did in 2006. So he redefined characters with the approximate factorization property, and he showed that if they satisfy this condition, then the associated random Young diagrams, they not only satisfy law of large numbers, but also central limit theorem. Okay, so any questions so far?
So is it another proof of Kerov's theorem?
Yes, so yeah, I should mention, so of course, these two examples, I've chosen them carefully so that they both satisfy the approximate factorization property. And it's also very easy, so if you look on the definition of cumulant, the higher order of cumulants for the regular representation, they're just 0. So yes, and for sure-while measure, it's also very easy to compute them and to see that they have the approximate factorization property. So yeah, indeed, this is a generalization of Kerov's theorem.
So is this stronger than the previous approximate factorization, the two?
I mean, yeah, the condition is more restrictive because you don't have to check only the first and the second order, but you have to check all the orders.
But at least in the two cases.
Yes, because a priori, I mean, if you want to have a central limit theorem, first you have to have a law of large numbers. It makes sense. Okay. So now I'm going to the second part of my talk, when I'm gonna explain you that the picture of the representation theory can be replaced by the picture of the symmetric functions. So in order to do this, it's enough to know that the sure symmetric function, if I expand sure symmetric functions in a power sum basis, the coefficients are just irreducible characters of the symmetric group. So this is not, of course, this is not a standard definition of sure symmetric functions. This is a property that you can prove. But this is the most important property that we need for our purposes. Here is one of the more standard definitions. You can define sure symmetric functions as Gram-Schmidt orthogonalization process applied to monomial bases. So in order to do this, you have to define a scalar product. You're defining it in the following way, that the power sum basis is orthogonal. And then if you apply a Gram-Schmidt orthogonalization process to monomial, what you get is a sure symmetric function. I don't like this definition very much because it's not very, it's not informing you too much what sure polynomials look like, but it has one advantage. It's easy to see that you can put some parameter here and you can pretty much write exactly the same definition, and you will get a new family of symmetric function which can be treated as a one parameter deformation of sure symmetric functions. So this is a definition of Jack symmetric functions, and the definition is pretty much exactly the same, except that now your scalar product has this parameter alpha. So you can think that alpha is some positive real number, and when alpha is equal to 1, you obtain exactly sure symmetric functions up to this normalization constant, which is n factorial divided by dimension of lambda. If you're a combinatorialist, maybe you don't like this definition, so it's much better to have a formula. So of course you know that, probably you know that sure symmetric functions can be interpreted as a generating function of semi-standard Young tableau. So it would be really nice to have a similar formula. And it turns out that there exists a combinatorial formula for Jack symmetric functions that I'm going to show you right now. So I need some notation. If I have a box U in a Young diagram, I denote by D of U a box which is lying directly below. And I also need to introduce a definition of a pair of attacking pairs. A pair of attacking boxes. So two attacking boxes in a Young diagram are boxes which are either lying in the same row, or they're lying in two consecutive rows, such that the box which is lying in a lower row is lying strictly left on the other one. So let's see which boxes are giving an attacking pair with this one. So of course you can take all the boxes in the same row, and you can take two consecutive rows. If you are in a lower row, you have to take a boxes which is on the left side, and if you go above, you have to be on the right. Okay, so we are ready to state a formula, a combinatorial formula for Jack symmetric functions. So what is this? You need to sum over all fillings by a conjugate partition to lambda. So a conjugate partition is a partition which is obtained by reflecting by x is equal to y. And what does it mean that the filling is non-attacking? It means that whenever you have an attacking pair, then the entries has to be different. That's the condition. Okay, so you're summing over all non-attacking pairs. You're associating a monomial with your filling. And then you're associating a certain product which looks like an alpha deformation of Hooke. So for instance, this theorem tells you immediately that, that if you want to expand Jack symmetric functions in monomial basis, the coefficients are polynomial in alpha with non-negative integer coefficients, which was an open problem in Jack symmetric functions for a while. All right, so here is an example. I hope it's I really hope it's non-attacking filling. You can check it. One condition that you can that you can check for sure is that in every row, all the entries should be distinct, right? Because if there are if one entry will be the same, it means that it's definitely an attacking filling. Okay, and by this green circles, I indicated these boxes, which has the property that the box just below has exactly the same entry. So for these boxes, I have to associate this funny product of alpha Hooke deformations. Okay, so this is how the formula for Jack polynomials works. And maybe the last comment for those who likes McDonald polynomials, Jack polynomials can be seen as a specialization of McDonald polynomials. So what you should do, you should take an integral form of McDonald polynomial, and for q, you should put t to alpha. You divide it by 1 minus t to the degree of the polynomial, which is number of boxes in lambda, and you take a limit t is equal to 1. Okay, so now if we know what are Jack polynomials, we also know that that we can think about them like a one-parameter deformation of Schur. It's actually quite natural to define irreducible Jack characters. So what you have to do, you just have to take the coefficient in a power sum basis. Then you have to put some normalization constants so that it has this property that when alpha is equal to 1, you just have exactly irreducible characters of the symmetric group. And then we pretty much repeat the idea of Philippe Biane. So we can say that if we fix alpha and we define this reducible Jack character, there is a one-to-one correspondence between random Young diagrams of size n and reducible Jack characters. So we can define some one-parameter deformations of some measures. So here we have exactly the same examples as before. So my function chi, it's the same here and here as before. But now I have this parameter alpha. So if alpha is equal to 1, this is exactly the Planchard measure. This is exactly the Schur measure. But if alpha is not equal to 1, I have a new measure. So this measure is called the Jack-Planchard measure, and this measure is called the Jack-Schur measure. It's not very original name. And they both have a very explicit formula. So you can see that this is like an alpha deformation of a hook length formula. Here I have this H alpha that I will show in the next slide what it is precisely. And here I also have this hook length. And I also have these two funny things. So this is an alpha deformation of a content of a box. So typically content of a box is just the difference between x and y coordinate of a box. And here there is some parameter that I will call gamma. It's just square root of alpha inverse minus square root of alpha. Okay, so this is an explanation of this deformation of a hook. So now I have two hooks, and they are pretty much the same except this last part. So here I add square root of alpha, and here I add square root of alpha inverse. Okay, and then we are able to prove the following theorem. So we can prove that whenever you have a family of reducible Jack characters, and then there is one condition which is basically telling you what is the growth of alpha. It's a bit technical condition, but roughly you can think that it's telling you how fast alpha can grow. And if they have the approximate factorization property, then we have a lot of large numbers. And there is one slight difference. So I told you about this scaling. So in the previous picture, we were scaling our Young diagrams in a way that its shape was exactly the same as the beginning. It was just smaller, so that the area was equal to 1. Here we are changing the shape a little bit. What we are doing, we are stretching it horizontally by square root of alpha, and we are crushing it vertically by square root of alpha. So each box is replaced by a box which looks like square root of alpha divided by square root of n, and 1 divided by square root of alpha times n. Okay?
But alpha is square root of n by itself, or what?
I'm sorry?
So what happens with alpha depends on n. So what is square root of alpha divided by n?
Well, so alpha might depend on n, but for each n this is some number. So it makes sense to look on a profile of such a.
What is asymptotics as n goes to infinity? What is asymptotics of square root of alpha over n?
So the asymptotic is given you by this condition. So this is why I said that there is a condition that alpha it cannot grow like arbitrarily. There has to be some kind of condition. So basically, this condition is telling you that alpha should not grow faster than n. Okay? So maybe you will see an example. I will show you two examples when alpha is fixed and when alpha is growing, so maybe it will answer your question a bit better. Okay, and this is the central limit theorem. So it's exactly the same as before. So we have the same condition. We want that our family have the approximate factorization property, and then we can prove that we have the central limit theorem. So now let's look on examples so that we see what's happening. So when alpha is fixed, then both measure, Jack-Planchel measure and Jack-Schur-Weil measure, they converge, the associated random Young diagrams, they converge to exactly the same shape as before. So this shape doesn't depend on alpha at all. So for instance, for any alpha, we have exactly the same shape. But as I said, we have this double scaling limit theorem, so alpha doesn't have to be fixed necessarily. And an interesting choice is when you choose alpha of n is equal to 1 divided by c squared times n. Why this is interesting? Because then we can actually easily draw this scaled Young diagram. So it looks like that. It is just a collection of rectangles. All these rectangles, they have the same height, g. So g is equal to c. This is this parameter that I fixed. And then they're just looking like lambda 1, lambda 2, lambda 3, and so on, but they are scaled by g times n. So then the limit shape of this random Young diagram, of course, it depends on this parameter g. And this is actually an interesting problem to describe this limit shape in a concrete way. But this is an example of the limit shape for c equal to 1 divided by 4. So for instance, you can see that it doesn't look like a smooth curve anymore. It necessarily has to have this staircase shape. Okay? Okay, and of course, it's easy to check, as before, that these two characters has the approximate factorization property, so we also have the central limit theorem. And there is also one more theorem which is telling you that you can produce more examples if you already have some. So this theorem is telling you that all the classical constructions which are coming from the representation theory, you can kind of mimic in the symmetric function world, and then you can just construct new characters. And if you start from characters which has the approximate factorization property, then your result also has the approximate factorization property. So you can define the restriction, the induction, outer product, and the tensor product. So if you already have some examples, you can construct more examples. Okay, here I just wanted to mention a very beautiful conjecture of Stanley, which is still wide open, and it's quite old. So, for instance, the outer product we are defining by using multiplication of Jack polynomials. So, if you look on the structure constants of the Jack polynomials, Stanley conjectured in 1989 that okay, up to normalization factor, there are polynomials in alpha with non-negative integer coefficients. And this is still wide open. So if you have any ideas how to do it, it's a nice conjecture to attack.
So it's unknown that it is a polynomial?
Yeah, it is known that it's a polynomial.
It is known.
Yes.
So non-negativity is a conjecture.
Non-negativity is a conjecture. Okay, any questions so far? Okay, so now I'm gonna go to the more algebraic combinatorics part. So what is the main tool for proving this theorem? So the main tool is a certain algebra and understanding more or less combinatorics of this algebra. So this is an idea which is due to Ivanov and Olshansky in a case of alpha equal to 1, which is just normal characters, not deformation. And they had this very, very nice idea of looking on characters in a dual way than typically. So typically what you're doing, you're fixing your representation, and you treat character as a function on the group. But you can basically switch role of representation and element from the group. So you can treat character as a function on Young diagrams in a way that you fix elements from your group, and then you're wondering what's happening if your variable now is an irreducible representation. So this is exactly what they did, and it turns out that if you define these functions, you have to normalize them in an appropriate way, but then they generate an algebra. And this is a very interesting algebra, and understanding this algebra is the crucial thing. So here we are doing the same thing. We are defining these normalized Jack characters, and we are defining them as a function on a set of Young diagrams. So the definition is pretty clear what to do. If your element from your group is smaller than your Young diagram, then it lies in a smaller symmetric group, so there is no problem of defining it. You just have to add some fixed points, and if it's bigger, you just set 0. And then this is also important to put this normalization factor so that it has a nice structure of algebra. So this algebra has a gradation, and the gradation of the basis, so basis is gamma to k times normalized Jack character, is given by k plus this norm of pi. So norm of pi is size of pi minus length of pi. Okay. And here is a very interesting problem. The problem is the following. So if you take the normalized Jack character, you can look on the top degree in the following scaling. So you're taking your Young diagram, you're scaling it by n horizontally and vertically, and it turns out that this function is a polynomial in n of degree k plus 1. So if you divide it by n to k plus 1 and you take a limit, you have a function which is defined on the set of Young diagrams. And we can prove that this function, which is called the free cumulant, that first of all they generate our algebra, and their degree is k. So we would like to understand how to express Jack character in terms of these free cumulants. And here is a table. So there are some things which are obvious from the definition. So the first obvious thing is that if you set, for a second, if you set that gamma is equal to 1, so you forget about gamma, then the top degree is given by rk plus 1, and everything else has a smaller degree. That's clear from the definition. But we can also notice one thing. So if you look on it, it's very natural to make a conjecture that all these coefficients, they have to be polynomials in these free cumulants and gamma with non-negative integer coefficients. Here I also indicated the top degree part. So the degree of this part is equal to 5 in this case. So you can see that it's R5. Here it's like gamma degree is 1 and 4, 1 plus 2 plus 2, 2 plus 3, and 3 plus 2. So this part is the top degree part. Now I'm going to tell you what we know and what we do not know. We do not know much. So there is a conjecture of Lassalle which says what I just mentioned, that this is a polynomial in gamma and free cumulants with positive integer coefficients. We only know that this is a polynomial with rational coefficients, and we also understand this top part that I highlighted. Okay, and this top part, we understood it in terms of something which is called maps. So this might be a big surprise for you, because if you remember how we defined Jack polynomials, they are defined in a bit abstract way by some Gram-Schmidt orthonormalization process. So there is no clear reason to see maps in this picture. but they appear. So let me explain you what are maps. Roughly speaking, map is just a graph which is drawn on a surface. So surface for me can be orientable or non-orientable. I want to say it because some people only treat maps as orientable objects. And my graph is drawn in a surface in a way that if I cut the surface along this embedding, I obtain a collection of open disks. And there is one important concept. I'm going to work with rooted maps. So rooted maps means that I'm distinguishing a corner in my map. So here on these three pictures, I'm indicating it by a red arrow. This concept is important in enumeration of maps because it's much easier to enumerate rooted maps since they don't have symmetry anymore. Okay, so when I have this bipartite map, it has naturally associated three partitions. So the first partition is a degree of white vertices. The second partition is the degree of black vertices, and the third partition is a degree of faces divided by 2. And when we're trying to understand Lassalle's conjecture, then we found a very beautiful conjecture, much older conjecture of Goulden and Jackson, which already hint a connection between Jack polynomials and maps. So let me show you this conjecture. So first, I'm starting from Cauchy formula. So this is a classical result of Stanley, and it's telling you that if you look on the following generating function, so what's happening here, I'm summing over all integers, then I'm summing over all partitions of size n. I'm taking a product of two jacks indexed by the same partition, but these jacks are in different alphabets. So the first one is in X, and the second one is in alphabet Y. And then the theorem, the Cauchy formula, it tells you that it's given by this Cauchy kernel. And if you want to express it in power sum basis, it's the same. So here I'm using P, Q, and R for a power sum in X's, Y's, and Z. So you don't have Z here anymore. But this is what Goulden and Jackson were interested in. So they changed this generating function by adding one more jack. And it turned out that this small change is giving you something which is much more complicated. So here is the conjecture. The conjecture says that if you look on this generating function, and here there is a very small combinatorial trick. So we are taking logarithm and you are taking derivative with respect to t. If you're a combinatorialist, then you can recognize it as a trick to go from enumerating labeled object into enumerating of rooted objects. So this is a standard combinatorial trick to go from one generating function to another. And then conjecturally, this is a generating function of all bipartite maps. So look what's happening here. So I'm summing over all bipartite maps. T is telling me what is the number of edges. Let's skip this B for a second. P is telling me the degree of faces. Q is giving me the degree of white vertices, and R is giving me the degree of black vertices. There is this funny B thing here. And conjecturally, there exists some funny statistic on set of bipartite maps, which is measuring if your map is orientable or non-orientable. So it has this property that it's 0 if and only if your map is orientable. So what is known? Not that much, actually. So the first result was due to Brown and Jackson, and they proved the following specialization. So first of all, they specialized R to 0, 1, 0, 0, 0. So what does it mean combinatorially? It means that you are killing all the white vertices except the vertices of degree 2. So why are you doing this? Well, it's because then you don't have bipartite maps anymore. You just have maps. It's a trivial bijection between maps and bipartite maps where white vertices are all of degree 2, just by drawing a white vertex in the middle of any edge. So that's the bijection. Okay, so first you're turning to not bipartite map, and then you're forgetting about tracking faces. And then they were able to prove that such a spatialization is indeed a generating function of maps. So now we have maps, and now we are tracking only vertices, only degrees of vertices. And a bit later, Lacroix, he strengthened this result. So he was able to track number of faces. Okay, so now the specialization for P is you just put some variable P, and you are tracking number of faces and degree of vertices. And then there were some other results, not in this spirit, but more algebraic in nature. So Kanonikov and Vassilieva, they proved that certain coefficients are polynomials with non-negative integer coefficients, but they're very, very special. So you see that it's Pn here, Rn here, and only mu is arbitrary. Then 2 years later, together with Valentin-Ferret, we proved that all the coefficients are polynomial in B with rational coefficients. So polynomiality was not known. It was only known that this is a rational function in B. And finally, Kanonikov, Promyslov, and Vassilieva, they proved that a certain coefficient, if you multiply by automorphism, by some factor, this is a polynomial in B with integer coefficients. So you see that there is still a lot of things to do, and this is a work in progress, so this is not completely finished, but together with Guillaume Chapuis, we can prove the following specialization. So now, the only thing that we have to specialize is R. We cannot fully prove the B conjecture, but almost. So for R, we are putting the same variable R, but we are able to track degrees of faces, degrees of white vertices, and number of black vertices. So with this specialization, we can prove the B conjecture, and there are some nice consequences of this formula. So for instance, we can also interpret this in terms of branched coverings of the sphere, and it also gives rise to B deformation of Hurwitz numbers. Okay, so there is still a lot of things to do. The P conjecture is not proved fully, so if you have any ideas what to do, please help me. And there are some perspectives. So first of all, we would like to understand this limit shape in the double scaling limit. So this was related with Alexei's question and this picture that I showed you. We cannot describe this scaling limit explicitly. So that's one of the things that we would like to understand. The second thing is that also computing covariance of normal distribution in this double scaling limit, this is strictly related with enumeration of these maps. So, and it's due to this conjecture of Lassalle, where we already know that the coefficients, they should have an interpretation of terms of maps. Actually, computing of the covariance matrix, this is related with enumeration of some maps, but we don't understand them fully. The third thing to understand is that there is this very nice result of Biane and Huang, that in the case of Jack-Pranchal measure, the joint distribution of length of rows are given by beta Tracy Widom. So the question is, how does it work for our model? I mean, is it still true that in our model it's the same, or maybe we can, I don't know, find a subclass of our model which satisfies this? I don't know. And finally, there are some other models of discrete beta ensembles. So at least I know two. One is due to Alex Moll, and also due to Borodin, Gorin, Guillaume. And they're all a little bit different. I mean, they all for instance, they all cover Jack-Plancher and sure value measure, but a priori, it's very difficult to understand what is the relation between all these models. So that would be nice to know more. Okay, so that was it. Thank you very much.